Welcome everybody. I just want to remind everyone that this talk is going to be recorded, and this is in general jointly sponsored by Technology Association of Oregon. So today I am introducing Heather because Alan is not able to make it. So it's a pleasure to have Heather Knight present in this forum. She has been an assistant professor at Oregon State. She has a postdoc from Stanford and a PhD from Carnegie Mellon, and MS and BS degrees in MIT from electrical engineering and computer science. So she has done something in top 3 ranked universities in computer science. Outside OSU, she also has this robot theater company called Marilyn Monrobot, which features robot comedy performances and annual robot film festival. So if you haven't been to them, you should definitely try that. So without further ado, I welcome Heather to start up. Thank you.
Well, yeah, thanks for the introduction, Prasad. It's a pleasure to be talking to everybody. This is my 5th academic year as an assistant professor in computer science, and one of the core faculty in the robotics graduate program, and as well as our new AI named graduate program. So lots of exciting things happening in the space of robotics and computer science, among other things here on campus. What's been happening the last couple of years in terms of the pandemic has been really interesting for me because I got in the field as an undergraduate researcher, big fan of undergraduate research. And January was my 20th year in robotics. So my field has gone from basically science fiction to reality, where now we have all of these robots running around on campus and such. So it's a great time for all of y'all to become social roboticists. All right. So what are some of the things that you will want to know in your new career as social roboticists? Gail, Prasad, Tina, students. So one thing that we need to understand when we're trying to make robots kind of coexist in human society is that they have to share spaces. And I'll show you a video in a second. But in order to do that, we have to model basically what are normative behaviors between multiple agents and shared human spaces, or even in the next video, we'll see like cars and bicycles, pedestrian spaces, a lot of different types of vehicles of various levels of automation versus like human driving working together. So in order for those systems to flexibly cooperate, they need to be able to make estimates of each other. So robots can try to estimate what a person is going to do, what they want. They could be carrying a tray of food and look around to see the people that are most excited about eating, or even detect gestures, or we could even train the people, right, to do gestures in a way that would be easy for a robot to detect. We also have to create behavior systems that are fluent and make sense to people. People get frustrated easily with technology, it wastes our time, or that is rude, or that just is breaking social rules, right? So being able to flex to the particulars of those expectations in particular contexts is really important. And the way that we make that happen is by deploying systems and surfacing those expectations so that we can design those abilities into the system and expectations. And finally, one common thread throughout all of the examples I will give you is the importance and role of communication. So the ability of robots to do things in a way that people can interpret, and the ability for a person to be able to tell the robot what they want them to do, or vice versa, right? In collaboration, you need to have both agents working together. So I'm using the word agent as a super category for something that has its own directives and can adjust its plan to achieve them. Okay, so let's look at an example. So this is a project that I did with Ford during my postdoc and with a couple other students at Stanford, where we were trying to establish what are the pedestrian rules of the road, like what. So in at least on highways, we write down what the rules are for how people should drive, right? And there's still like legal structures are made for humans, so they're not necessarily made for autonomous driving or computational systems. So there's still a little bit of extra work we need to do when we make machines operate in those spaces, but there's also a lot of really unstructured social spaces, such as sidewalks and so on, that that have a lot of implicit rules that we kind of need to model in order to make robots be able to exist in those spaces without causing problems. So one of the things, I'm going to show you that video one more time. One of the things I want you to pay attention to is we were talking about agents and trying to estimate what other agents are doing. So people were not expecting this robot. I call it the robot duck crossing the road. They were not expecting this robot to suddenly shoot out in the middle of traffic. You could think of a kid following a ball right into out into traffic. Hopefully people see it, right? But as soon as you see it, we are able to make adaptations and changes to what we are doing. And so this is kind of the human side of people that have no expectation that there's a robot that's going to pop out. How do they decide what to do with this system? So I want you to watch the bicyclist and the cars. So the bicyclist, super agile, first one to stop, has great situation awareness, right? Can really see when it's moving, like the robot's on the far side, so she keeps going pretty soon. That other car is like not quite so sure, like that robot is done. It's a little confusing, right? It's still in the road, so it's already been doing unpredictable things. So we have this history of what it has done so far. This is an erratic robot. I don't know what it's going to do next, right? But it stays in place long enough that eventually that human driver is like, okay, I think it's staying there, right? And we constantly have to make these estimates of each other in order to be able to take action in the real world. And so this I would call as an example of bystander interactions. There's no vested interest in any of these agents like forming relationships with each other. We're just trying to share a road. Okay, so I am a social roboticist. I also work in human robot interaction. I'll define those in a couple slides. But one of the premises of my field, my primary field, social robotics, is that people anthropomorphize robots. And that happens even when robots have simple forms, right? So on the left, you see this poster from DC like 10 years ago. Now everyone has kind of drones, videos, and so on. But at the time, this person had lost their drone and they were posting a award, and it reminds me of like a missing cat poster, right? So I've also had coworkers that have come home to their Roombas like in a big pile of dirt because they knocked a plant over, and all they saw was this robot with like puppy dog eyes being like, I'm so sorry, I messed up your house. Like, don't get me in too much trouble, right? So these systems do not need to look like people to cue those sort of behaviors. In the same way we saw in the previous slide, that system did not need to look like an animal or like even like another car necessarily to be able to pop into our ability to estimate what something is likely to do next based on what we can posit of its capabilities and based on the history of what we've seen it do so far, right? So this relates to a concept from social psychology, philosophy, various other things, a child development called theory of mind, right? And that is not an ability that babies, your very young children have yet. I think people start getting it around 4 years old. Like they do experiments where they move, there's two hats and they move an object from one hat to another. And a young child, like the caregiver might leave the room and come back. And the young child thinks that the caregiver has the same mental model as that child. So even if they've left the room and come back, if the child has seen that object switch hats, they think that the caregiver will know that. Right. So this is something that happens a little bit later in our social development as humans, this ability to like make estimates of what the other agent thinks that is different than our own. Right. But that ability is very helpful in designing human robot interaction systems bidirectionally, because I can have robots do things in a way that humans are likely to be able to perceive and understand so that they can make good decisions, right? So it's not always about pedestrian spaces. We'll also talk about examples from factories, like where there are moving robots and forklift drivers and humans that are trying to get their job or go on their lunch break. And so how do you make all of these systems work together? So the other metaphor I like thinking about with theory of mind is playing catch, right? It's not enough to throw a ball, right? The other person also has to catch that ball, right? So when we design human robot interaction systems, we need to think about, and I do this in my social robotics class. Sometimes we play catch like early on in the term, just because you have to so how did you decide who to throw it to? Were they paying attention, right? So you can also make decisions and choices about who to toss the ball to based on your estimate of what their attentional state is, and maybe if they haven't had a turn in a while, and so on. So so theory of mind is a really cool concept and across some of these applications. All right, so before we go into robots, let's zoom out, right? I said that people anthropomorphize robots. Okay, so why do we do that? Like, why are we even social at all? Like, why are we trying to estimate what the people around us or the agents around us are doing? Why have we evolved to do those things, right? And so it turns out that any social animal has the ability to basically track complex social grids, relationships like favors, fairness, a lot of different kinds of interesting concepts. And there are a lot of benefits to being able to get along with each other. It means that not everyone has to grow their own plants and hunt their own food and make their own clothes. We could live in community and distribute tasks. We might even enjoy each other. In animal behavior, like in primate behavior, social grooming, like the pulling of bugs out of the other ape's fur, predicts whether likelihood of protecting someone in a fight and also likelihood of mating, right? So there's lots of things that interact in terms of humans as social creatures that have made us dedicate a lot of brain space to tracking social grids as well as communication. So I also occasionally do work, or really more my students, in human-computer interaction. So let's look at HRI and HCI from a human-human communication system. What are human-human interfaces, right? We have our senses, we have our ability to move. So we have like sense, sight, so on. But also we have this really neat brain, right? And apparently, I'm not a neuroscientist, but of all the wrinkly bits on the outside of our brain, a lot of that is dedicated to social processing. We also have parts of our brain that are about detecting faces or potentially even biological emotion. So some of our understanding of neuroscience behind all of this stuff is really interesting, but it turns out if you are a healthy, socially functioning human, you cannot avoid anthropomorphizing little Pixar like shapes moving around on the screen and so on. This is really fundamental to being human, that we have these communication interfaces and ability to track and estimate behavior of other agents. Cool. So my work contributes to two main fields. First, social robotics, the one where we use metaphors of how humans interact with each other to tap into that parts of our brain, right, that can do that kind of predictive analysis and communication. So that just makes for more efficient, intuitive interfaces. And sometimes more importantly, you can avoid offending people by following norms, right? So sometimes there's a bigger risk in doing things badly than there is doing things like kind of well, right? Like if there is a restaurant that you go to that has okay soup and you're hungry enough, you might go back. But if you found like a glove and and several flies in your soup, you not only will not go back to that restaurant, but you might even like call the Department of Health and close it down, right? So it's really important to not do things socially wrong, especially in those coexisting spaces where there are other issues like safety or comfort, like customer service. Like if you there have been robots fired from grocery stores because humans found them creepy, right? So it's important to model these things. We also contribute to human robot interaction, which is the super field, right? So that can also include interfaces. There's a lot of rising work in human in the loop systems because of some of the complexities of human in their environments, like pop in a human when the robot gets stuck. And that's really how the Starship technology robots work. I have heard that there are student workers that are hired by campus dining services that are helping drive those robots. Someone help me find out if that's actually true. But they're definitely human in the loop systems. They're not autonomous, or they might have some autonomy. Cool. And no matter what, the way that you finalize your design of this system should be through testing them. So here's just an example of simple communication between a human and a robot system, very intuitive, right? Like, come over here, like the kind of signaling we would use with each other. If you can get that end-to-end system working, very intuitive, does not require every human to become a programmer to use robots, right? Like it's easy to put these things in different environments. All right, The last thing I want to say for the intro before we get into the body of the presentation is just the changing paradigms of robotics and automation. Yeah, so in the 1970s, it was really popular, this concept of the lights out factory, where so much of the manufacturing process was automated that you didn't even need to have lights in factories anymore. It would just all be robots. Manufacturing has really shifted, right? So I went to visit the Volkswagen factory once in Germany, and they said that about 50% of the car manufacturing work is done by humans. So there's some parts that machines are really good at, like punching out the metal that shapes out the outside of the car. But there's some other things, even like getting the car seat to like do that like weird parallel parking thing to get into the body of the car, that people are still a little bit more adept at doing, because the car can present in slightly different angles and so on. And so some of those things, as technology improves, I feel confident that we will be able to get a car seat into a door. But other things might be cheaper, or just human dexterity, like sewing on, like for the fancy cars like BMW, sewing on the leather on the steering wheel. Like that is something that is still done by humans. And there's a rising set of opportunities that are kind of in the middle, right? That could be done by humans and robots together. So imagine that human putting in that car seat and then a robot coming in and doing some rivets, like, right? That could happen, and it might be more efficient because you're leveraging what the human is good at and what the robot is good at. But that only works if these systems are safe, right? And safety is both literal and perceptive. Like the person has to feel safe next to it, or there's no one that's going to actually use that in their factories. There's also just been a rise of just adding sociability to other types of technology and so on, which this is all a big part of. The final bucket is this idea of using technology to help us meet our own goals. So basically tapping into social psychology to do things like, it's easier for humans to get things done with other humans than by ourselves. So there are also rising applications in things like coaching, even for writer's block or musician's block, like having a system that could sample music or so on, from which that we can do creative collaborations across human and machine systems. Or even memory support, right? To help give reminders. I use the reminder app on my iPhone all the time, but if you can also add some sociability, you can sometimes tap into helping us become the people that we want to be, right, through these systems. Cool. So in a little bit, I'm going to talk to you about 4 different projects, mostly the first 3, agricultural robots, this logistic robot, so the robots in factories, then they go to trucks, then they go, last mile to your door and so on. I'm mostly going to talk about the factories. Then we'll talk about some applications for examples of service robots that can exist in our everyday spaces, 3 examples from our campus. And we'll finish with a newer project that we're just getting started on assistive and social feeding. But first, I wanted to tell you a little bit about my background and what my lab has been doing and some of the things at OSU. So I'm excited about this because it was just last month. I started as an undergraduate researcher at the MIT Media Lab. My advisor was Cynthia Brazil. I ended up staying and doing a master's there on the Sensate Bear, I was an electrical engineering student as an undergrad, and so we designed a system of sensors that could detect real-time touch, so gestures. So as soon as you hand someone a teddy bear, they kind of expect it to behave a little bit like a pet or a baby or so on. So people would like give it a handshake, they'd pat it on its head when it did something good. And so basically I used some of my experiments to first establish the distribution, like the density of the sensors that were required to be able to detect the kind of gestures that people expected the bear to understand. And then run follow-up testing to verify that it was actually able to complete the recognition of those gestures. So it was really fun. I kind of went from something that had been previously intended to have like 1,200 sensors to something that had more on the order of 50 sensors. So it was fun. I think that like computation is faster now, but it was fun getting a real-time system that worked for that particular platform. I also worked at a startup, Aldebaran Robotics, that made the Now and Now Pepper robots in France. It's since been acquired by SoftBank Robotics in Japan. Did a 1.5-year stint at the Jet Propulsion Laboratory looking for other like planets in the extended universe, or at least contributing to the instrumentation. that would do that, and also doing 10% time in some of the robotics projects, as well as some of their like interactive art installations. We made like a interactive thing at the AAAI conference at Caltech, where we had we use the brightness of people's phone to let people in the audience control these comments that were making things explode. We were trying to think about get people at the AI conference to think about applications of AI to space technologies, pretty broad. Also got to do some really fun projects with SynLabs, which was a group in Los Angeles doing interactive art installations for events and parties, and eventually we made a music video with OK Go, which I don't have time to share, but if you can look up This Tool Should Pass, it's a giant Rube Goldberg machine. I'm teaching applied robotics next term, and a Rube Goldberg machine is one of the things that the students get to design around their little robot. Did my PhD at Carnegie Mellon and a brief postdoc at Stanford. This is my life in one slide.
It looks like your video has frozen. Can you
so I looked at XY robots, so mobile. Sure. Thanks for letting me know. Let me see. What can I do about this? How is it now?
Okay, yeah. Go ahead. You're still muted. Can you?
Anybody?
Yeah, looks good.
Awesome. All right. Thanks. But basically something as simple as changing the way in which the robot is traveling down the hallway can change its characteristics from kind of looking like it has plenty of time, definitely is carrying a basket of candy on Halloween, like definitely open for people to come take candy, whereas this other robot, it's really looking like, oh, it's on the way to a meeting or something. I'm not going to interrupt it. So it doesn't stop everyone from taking candy, but people were almost, I think like 3 times as likely, if I remember right. We'd have to look at the paper. It's been a long time now, to take candy from the accessible looking robot over the one that looked rushed. So you can also basically shift the how of a robot doing a particular thing, like path planning from here to there, and that will shift the way people along the way interact with that system. Okay, let's see. So I'm not the first person in the world to think about this. Psychologists and then neuroscientists started looking at when people attribute agency to inanimate forms and objects since a long time. And I think we kind of covered this a little bit in the intro, but so here's one of the earliest studies that I know of. So it's called, the paper is Do Triangles Play Tricks? But basically every single person in their study attributed storytelling and character to these little guys, right? And so one of the big differences between when humans interpret something as an object versus an agent is when something moves with intent, following its own impulses. So basically, as soon as you now like alive, right? Because it's making decisions about how to get around objects. Another set of work that I did during my time at Carnegie Mellon was some attempts at doing robot comedy. It started out as a system seeking to estimate the audience reaction and then put that data back into its kind of Netflix algorithm of what jokes it would then deliver the audience using online learning, which is a little slow, but it was still a fun demo for how you could incorporate audience feedback, which I was arguing is easier to track than individuals have high variance, but audiences, there's a lot of social structures in audiences in terms of when people applaud and so on that you could leverage for the robot to get good estimates of the human reactions, aggregate reactions. And so we also use some of that work to do a robot tour guide project for a little bit. But yeah, so this was another fun one. And then I ended up doing a lot of robot comedy in various locations for a little while and talking to comedians, and learned a lot about how performers would make recommendations for a robot to do behaviors in a way that would be compelling for human audiences, which I think has a lot of cross applications in everyday service robots. So number one, I was just trying to make the audience happy. I don't know if that's more about me as a human or if that's all humans, but I thought the robot should serve the people, right? And they're like, no, the robot is in charge. It's the performer. It should lead the audience, right? So there was some power structure stuff that they suggested to me. They also suggested that the robots talk about its unique personality. So they liked, the audience really laughed at these lines. My perception system is still in development after it made some ridiculous assumption about the number of people in the audience, right? And that was a big laugh line. And there was also a collaboration I had with a CMU dramaturgy professor where he wrote some Shakespeare knockoffs, right? If you prick me in my battery pack, do I not bleed alkaline fluid? Which was quite popular. And then the final thing that I learned but didn't get a chance to implement as a student myself was the value of having a plan, but then also being able to adapt from that plan. So stand-up comics are great at making things feel live, but secretly a lot of that's pre-planned. But sometimes things like a waiter drops a tray in the audience and they have to do these quick adaptations, like where they can bring the audience's attention back to them, like, or even make a quick joke about that. And then there's crowd work, which is even more interactive. So that stuff it's good for you to know about, just because it might explain why we have made some other choices in our stuff today. So this is the music track from the game, the Oregon Trail. But anyhow, so this was my path. I've been at Oregon State since 2017. Here's a picture of my lab before the pandemic. Here's a more recent picture in our Web 3.0 hybrid lab, where my students surprised me at a lab meeting with lots of Zoom filters. So yeah, Charisma can be delightful in many formats. I'm not going to have a chance to talk about all of our work, about halfway through the talk already. So the two projects I just told you about, right, like expressive motion for simple robots, robot comedy, they've become many more projects. So some of them have turned into, I started working with a factory robot company, Auto Motors, and we had a 2.5 year collaboration, which I'll tell you about in a little bit. We've done some robot furniture that use some of that gesture work. I have a PhD student that's looking at multi-robot expressive motion, so that has its own extensions and complexities. I had an MS student even talk about collisions, so that's kind of the intersection of touch and motion. So tapping someone can be a nice way to get their attention without, for example, interrupting a larger social space. And so we'll talk about some of these examples. But then my students also come up with their own ideas, right? So we've touched a lot of additional things. So I had a student that was really into working out, who really wanted to make a robot health coach. I talked about the entertainment stuff I had done in the past with a student in my social robotics class that was on the improv troupe. So we had a paper about robots. We created a new improv game that incorporated a human and robot performer, and learned some things about gestures from the perspective of improvising performers and so on. And some of our stuff with robot furniture turned into a bunch of interface design stuff that opened up some new opportunities also in underwater robots, inclusive interfaces. So we've touched a lot of domains in the almost 5 years that I've been here. And I'm just one of 12 faculty in robotics, so there's a ton more robotic stuff on campus for y'all to check out, as well as the Chorus Institute, which is the Collaborative Institute for Intelligent Systems and Robots. I don't know, I think I got the words confused, but there's about 30 plus faculty in AI and robotics and we like doing projects together. And so that really begs the question, because one thing that I think is really great about both the robotics and AI named graduate programs is we have this ethics requirement that all the students take a class in the kind of application of our technology to our everyday lives. My attempt at contributing to some of that storyline was curating short films from around the world, from researchers and entertainers, or combinations thereof. Lots of music videos for a robot film festival. Our tagline was positive storytelling about robots. So you can check that out sometime. I don't have immediate plans to start it back up, but there's some really great archives. And one of the things that I thought was important is storytelling can help us kind of case test existing technology and play out how that might impact society. It can also help inspire technology designers to think of what to create in the first place. But one of the biggest things in terms of all of these years of audiences in New York City, San Francisco, Portland, Los Angeles a couple times, Pittsburgh, of course, Carnegie Mellon, was that the audiences often really just loved seeing our technology. So one of the things I learned is that if you were doing a cool project, make a video so that other people can actually see it, because they will probably enjoy it. The world is very curious about robots. So recently, this has been even more of a big deal, right? So I've been using this slide for 10 years, literally, like this idea of the 3Ds, the dull, the dangerous, and the dirty on the left, some of the motivating applications for robotics and automation initially, to the onset of robots in many, many more roles, like around in everyday operations around people. So Roomba sales robot vacuum cleaner sales have increased every single year since they were introduced in the 90s. There's entertainment robots, there's multi-robot systems, there's applications to support, inverted pyramid populations where there's many elderly people and fewer babies. Who's gonna take care of people? Collaborative manufacturing, labor shortages in hospitals or agriculture that robots can help fill in. And so this has already been a transition that's been happening for a while. But the last couple of years have really accelerated this trend. So if we just even consider our local companies, right? Campus and Dining Services acquired the Starship Technology, a contract with the Starship Technologies robots, which is founded in Estonia, but I just learned this morning is now headquartered in San Francisco. So those are the robots that are all around campus right now. We also have two really cool startups that are in logistics or in delivery. Agility Robotics, which is in Tangent, Oregon, a little bit east of here, and DAX, which I got to visit yesterday, and they're very, very cool. And they do food delivery, but with more social expressivity than the Starships. And so they have deployment locations in Philomath, and even a data sharing agreement with the local city council, which is awesome. At least I think so as a researcher, and also in Georgia. So a lot of these companies are expanding, and investment firms estimate that the cost of robots doing delivery is likely to supplant even the rise of the human in the loop driver systems. I'm sorry if this is the thing that you do to make extra money, but all of that data that things like Uber Eats is collecting about like trips and deliveries and is developing these interfaces for sending the picture to you and your email and stuff like that can also start including robots. So this trend is only going to continue. All right, cool. So let's just go into a slightly deeper dive of 4 projects, and then we'll let you all go. Okay, the first project is in robots in agriculture. So I'll mostly focus on robot pruning. Oregon State was one of the member institutions of a new AI research institute across a bunch of places. I think that the home university is Washington State University. To think about ways that AI and other tools like robotics could be applied to support the modern farmer. And one of the things I really love about our proposal and our 5-year plan is that there's a heavy integration of humans and the people that would then use this technology across all of the years of that grant. And in particular, adoptability is one of our principles of developing our technical systems. We want to create systems that the farmers would actually use. So the 3 areas in which we are trying to innovate is in water, weather, and labor management. So I'm going to focus on the last one because that's where the robots come in. So the 3 applications that we are explicitly looking into for like supporting agricultural labor forces with robots and AI and computer vision and stuff are pruning, thinning, and harvesting. So some of the things that we are seeking to learn in this first year of 5 in our formative design phase is what would actually be helpful to the growers and acceptable and useful and tractable. What is something that is actually of service to these systems? And this obviously will vary by plant, and even I'm learning tree canopy. Like there are now ways that people grow their plants in particular ways that require different strategies for pruning and maintenance. We're starting with pruning. So here are some of the systems that have previously been worked on and existed at Washington State University and Oregon State University that we're trying to get to actually work based on some of our analysis of what the farmers need, right? So we just collected our first human data. I can see Deanna, my PhD student that was there. But yeah, so one of the things that we learned is that people are super fast. Like they could prune 9 trees in 4 minutes. The type of plant and its canopy predicted several of the pruning rules, which is really helpful when we actually program our own robot pruning systems. But from the human perspective, one thing that I found really interesting and surprising is that the farm managers said that the robots don't need to be perfect, right? They don't even necessarily need to be as fast as the humans. What they need to do is reduce the workload on the humans. So if any of you have had a robot vacuum cleaner, that makes a lot of sense. Like they don't necessarily vacuum or sweep more efficiently than people do, right? But they help. And I might have to go back and spot check later, right? And that's kind of what their workflow thought is. Like you can have the robot do like a bulk or a significant part of that labor. And then you can have the humans that really want to finalize the details because they use the pruning to try to guess how much they will be able to harvest and the quality of that harvest. And that has to vary with what weather conditions are. So sometimes it's an iterative process. And so pruning goes into flower thinning, and then eventually down the line, there's a harvest, right? And then finally, in terms of interfacing, they do want to be able to vary some of the strategies for particular blocks of trees, or maybe there's a part of the orchard that's like downhill and has a lot more water. So they expressed it they didn't want to use screens, right? It was interesting to hear what they imagined a perspective interface with our system. So very early data, but it's an interesting project that illustrates a lot of rising opportunities for human-robot collaboration and meeting human needs, right? And also set some concepts for how to include human information into setting objectives for the system, as well as adapting things like in the field, like literally the field. And then of course, if we have good perception systems before and after some of this stuff, then we can also get into some of the more data-driven methods to validate, for example, if our pruning rules are actually effective. All right, example 2. Factory robots. So logistics is the super category for like getting all of the things from the packages and warehouses to our door or to stores or all of those things. So this kind of goes back to my open, right? Like sometimes to be able to contribute to a collaboration, you need to be able to coexist. So our first research site, and this is dating back to the first couple of years of my professorship, was at ClearPath Robotics, who are also the owners of Auto Motors, is their factory robot company. They also make a lot of other cool farm robots, mobile robots, and so on that researchers like to use. The first thing that we did is we went out there and we talked to the people at the company. I think there were about 150 employees at the time of this first study. I think it's extra 100 since then. Just like everyone else in robotics, things are really expanding fast. To basically find out what are the meaty problems to improve in these robots in terms of human-robot interaction, and also kind of use them as a data set for what is it, because they were an early system that is out in human spaces. So Ryan Callow is my main contact there, and he's the CTO. He was previously at Kiva Systems, which was what was acquired by Amazon to do basically, you could make buildings around robots, right? Like that, or have lots of things. But the goal of the Auto Motors robots was that these robots can cooperate around people. So you can go to a new building, you can drive them around in a grid. It's building a map. That map is now showing up immediately on this tablet interface. I could hand it to a person in the factory, and now they can just drive the robot around or drop a pin basically, and the robot can figure out how to get back to that. So within 45 minutes, it's set up and running in a new location, which is really freaking cool, right? But so they learned a lot about what their customers wanted, right? We also did a study of the employees themselves and their relationship to the robot. So like, for example, in terms of anthropomorphism, a lot of them didn't want to admit they did it, but when they actually explained why the robot made a mistake in something, a lot of the interpretations were very anthropomorphic. But yeah, there's a lot more in that paper. Feel free to read it. It's called The Robot Makers, an ethnography of anthropomorphism at a robotics company. But that first set of data collection led into a more kind of traditional engineering collaboration, or at least HRI engineering collaboration, where my student Alexandra Bacalo went out there for a summer and helped expand their light set design and evaluate some different potentials for expanding their light communications. So for example, I think they had some light communications for the robot that was about to turn and so on, but people got confused why when its task was actually complete versus when it needed something from a human and so on. So they added some state communications to the system that actually made it better able to meet its goals doing this factory transport, because often at the end, sometimes there's an automated thing that lifts the pallet off of the robot, but other times there's a person that needs to be the one. So that communication between these co-workers is something that's important. Alexandra also considered some different styles of light communications. The car-inspired signals are easy metaphors for people to understand without training. There's also this glowy thing that worked pretty well for certain types of things, and it was less intrusive if you're trying to do something that is like, when you have time, notice that I'm ready for you to pick this up, rather than like, do this right now. So you can choose different signals to fit your social goals, like for so on. And then also some like animations of lights, like I'm going to go this way, or like please get out of my way. So you can read more in the paper, but one of the really cool things is that the Auto Motors updated their software stack, and so now some of these light communications are running on robots operating in 100+ factories across North America. So impact, very cool. And my other favorite ClearPath story is that they created a impatience variable where the robot basically incremented until it hit a particular timestamp, and then would go around something that was blocking its path. And that was more socially acceptable than either going right around it from the start or waiting forever, because the robot still needs to get its job done too. So sometimes we try to test things out so we can see what is the right behavior for the situation. And then we are also extending some of these functional and social communication work to multi-robot systems. So stay tuned for that. All right. So in this section, I'm hoping that you will see that expressive motion is just one example of useful robot nonverbal behaviors. If you're going to make a mistake, fail in a way that seems socially competent. Lots of channels are available to robots, light, sound, but also the sequence of choices it's make. And robots don't always have to be nice, right? Sometimes impatient robots get stuff done. All right. Service robots. So we have had several deployments on campus of robots that are operating in our spaces. So the first one I'll tell you about is the chess tournament, where we had these 2 robot chairs that were trying to recruit people in the Kelly atrium to come and play a round of chess. And then we had a robot health coach that ran for 3 years in the graph building for the robotics students, where it would basically encourage people to do some exercise in the middle of the day and ask them how they were that day. And we also pivoted that project during the pandemic to a robot that was distributing hand sanitizer. So this is your interactive part, all right? And let's see if I can get you guys to pay attention a little bit. So here we have this experimental setup where we have 2 chairs, the black chair and the right chair. And so we explored a couple different motion styles of trying to recruit people to come and play chess. So I've also have this this interest in robots running their own human studies. So it's like fun to get the robot to kind of be the one persuading you to come and do things. So we're going to take a vote, and I think you can just write it right in the chat, 1, 2, 3, or 4 for what you think will be the most effective motion strategy for getting people to come and play a move of chess at the table. Okay, so if you think no motion is the best strategy to get people to come and play chess, it's the chair sitting a little out next to the table, then you can vote 1. If you think forward back of the table is the best strategy, vote 2. If you think that going off somewhere else in the atrium and trying to pull someone back in is the best thing, say 3. And if you think pulling out a little bit and spinning in place is the best solution, say 4. Cool. Well, I see some of my students in here, which is cheating, but but yeah, actually, this is a better distribution of guesses than many of the audiences. Like ClearPath got, like the employees there when I gave this talk was like, we got it completely wrong. But basically, the drum roll, please. The answer is so the most successful approach is forward back motion at the table, because it basically acts like an arrow vector that says, look here, look here, look here. Whereas the one that was spinning, which often is a popular choice, is like really terrible. We're seeing like 3%, 12%, 0%, and our behavioral vectors are, did they play chess? Did they go to the table? Did they sit on the chair? And that was because people were like, okay, I get that you want something, but I can't sit on you, right? Like it's hard to sit on a moving chair. So I think it was that, and spin ended up being really confusing. So confusion is really bad in human interaction. Like that means that there was not common ground, right? And approaching, we think, wasn't that successful, mostly because it just, like people were further away from the table and they had other things to do. And so it was just harder to motivate. But a lot of people just like coming and playing chess. So doing nothing was also an effective way, at least in the Kelly atrium, of getting people to come and play chess. The chessboard itself was good at recruiting people. Cool. So we've done some other projects that also help us explore and understand, because until you actually do that testing, sometimes the answer is really not obvious. But once you do, it can be a lot easier. So we were trying to understand how to support health. So for example, telling people a joke, asking them to do some exercise, and then offering them a healthy snack. And so we did 3 years. Our first year was just try to get a behavior that felt good and was fluent and that people enjoyed, as well as creating an interface that could scaffold that, make it easy for the wizard to actually follow. And here's a video example of how that actually looked. So there's a little camera, some motion gestures. This is improv, right? He asked for a high five.
Thank you. Oh, thank you, Resolution Bot.
So there's smiley face buttons where people could say how they were feeling. He said it's kind of between these ones, but I'll go with this one. Cool. So now you can hopefully imagine it. So like our second year, we looked at when people broke the script, either from the wizarding side, like for example, during that high five, like there's both a behavioral and a verbal script, right? Of what we know that we want to offer the participant, and then what they seem to want, or sometimes people were confused and they need extra cueing. So this was an interesting way to think about, well, how much does need to be planned and how much does need to be flexible? And then our final year, we assessed the system against some explicit social variables. People didn't find, at least for this 3-week deployment, that it had a major impact on their health, but it did have a significant impact on their experience of camaraderie and bonding in the workplace. So that was kind of an interesting result. So we've just submitted a paper about that as well. So during the pandemic, we pivoted this platform to also offer hand sanitizer.
Here is an example of the Starship robots helping workers on our university campus to deliver food during the pandemic. Many of such robots have explored ways to help humans in preventing exposure to COVID-19, but what most have not explored is how robot pro-social behaviors could increase people's compliance to safety measures during this pandemic. This video presents the hardware design of sanitizer bot and shares example of people interacting with the robot. As seen in this video, we define a robot to be pro-social if it voluntarily helps or benefits humans. In this context, this robot helps to prevent the spread of COVID-19 by distributing hand sanitizer. As seen here, for communication during interaction, our robot uses LED signals and speakers which enable interaction through light and speech, along with motion gestures and movement modalities. Sanitizer bot is designed to consist of a hand sanitizer dispenser mounted on a TurtleBot 2 robot fitted with LED light strips, speakers, and a laptop.
Cool. So that was a fun project and 2 master's projects about that one. But yeah, so we're writing a paper about that one as well. Stay tuned. The last application is much newer for us. We just started working on it last summer, but I'm kind of excited because I think it pulls together some of the other parts of what we've been doing so far related to expression, utility to humans, and also sociability. So let me briefly tell you a little bit about our early work in robot assistive and social feeding. So we've all talked a lot about motion and its influence on interaction in this talk. So we ran a quick experiment last summer. Well, we're a REU site in the robotics program, so we get summer students from around the country, and we ran in addition, after doing a literature search about the current state of robot feeding, which is mostly functional tools, we ran a study in which we tried offering food to people using different tools and different pathways. So I'll tell you about the results of that in a few slides. But what's unique about some of this stuff is that most of the work that had been done previously was really about physically manipulating food or the mechanics of an assistive feeding system, and much less work has been done about the social attributes of feeding. And when you have an implement coming at someone's face, right, that's sort of a high stakes task, right, from both a safety and potentially even a social empowerment perspective. And some of the work from my student Deanna, we have looked at some of the robot nearest neighbors for assistive feeding, which again is more about like manipulating particular types of food, but also doing some kind of neat early studies with populations that have, for example, arm mobility impairment, so they would need to do that feeding. And then also looking at some of the human literature of what is written up about feeding style and so on. But there's a lot of open ground for this problem. So in this particular experiment that I just introduced, what we used was this little tabletop mobile robot called the Burger, BRGR. We had a setup where it was the robot was on a table kind of behind like a little, almost like a stage-like mat. So it would come through the curtains and then come and deliver food at a particular time. So a lot of people have their own things to be doing, and they're not just waiting on a robot to come feed them. So we tried to simulate busy humans by having them watch the Olympics, which was which was running on an iPad during our experiments. It was within subjects, so each participant experienced all experimental variables. Happy to share the late breaking report with y'all, but the short answer is that both the tool type and the path type impacted whether people said that they were likely to take the food from that robot. So the spoon really added a directional element to the path. So it seemed like a little bit more aggressive. This graph isn't the only graph we have in terms of the human ratings of this system. But yeah, so when the system really seemed to care about offering feeding, perhaps that influences whether people are likely to take this. So this is very early work. We're going to keep learning more, but I think there's a lot of interesting opportunities for applying social expression and socially intelligent behavior to this task. There's lots of new hows to consider. For example, in addition to motion style, could we influence whether and what people eat? Could we explore mixed initiative feeding? Like, what is more socially normative? What's more empowering? Like, does the human want to initiate when we want to be fed? Does the robot initiate? Does it make sense socially for a mixed initiative approach? Hopefully you all already know the answer. We have to test this with humans to get that, to understand what the right path is. And another problem space is, how do you integrate this feeding application into a larger social structure such as a family, all working together, all talking together and hanging out at the dining table, because eating is not just a functional experience, it's also a highly social one. Cool. So thanks for coming to my seminar. Today's lessons covered a couple themes. You can't develop the human robot system without deploying your system around humans. So get your robots out there. It is important to consider what the human experience is when we create the human robot experience, because often that's the best proxy for achieving functionality and sociability. So it's a good first path. Robots are designed to support human objectives. So humans are often a really good place to start when we're designing them, like in those pruner systems. It doesn't always have to be exactly one-to-one, but we can take inspiration from what people do and take and leave the parts that are useful for robots to do, as well as continuing that testing to make them work even better. There's a lot of rising opportunities for human in the loop system. It's like cool right now. It used to not be cool, but now that robots are actually out and operating in the world, like, it's kind of necessary to get them to meet the meet the expectations that humans have of functional operation, because functionality, as we learned in that anthropology experiment at ClearPath, is human relative. So people think of intelligence as, well, what would the person do in that situation? And if the robot does something completely different, then it seems really like dumb, right? So there's a social influence of attributions to robots. So it's nice to know when not to do things to increase their value. Yeah, and finally, nonverbal signaling is incredibly powerful. So we covered a couple different topics, agriculture robots, which then can go in a box and be shipped to you, be offered to you for your fitness and dieting robot, and then perhaps even fed to your mouth. Okay, well, thanks for coming to my talk.
Yeah.
I am open for like
Heather.
2 minutes of questions.
Yeah, well, yeah, I have to leave at noon. I mean, if people want to stay after and ask questions, that's fine. Yeah, so could you get a robot to feed my kids broccoli? That would be a major research challenge, I think.
Yeah, I mean, I just need to get the IRB for children to be included in the experiment, but we are always seeking research participants,
Okay.
Alan.
Yeah. So does anybody have questions for Heather?
Yeah, hi, this is Kostos. So I am one of the students admitted for fall 22. So hopefully I'll join. So my question is, there was an interesting video about using gestures to ask the chair to move towards the table, towards the beginning of the talk, and also another one about the chess and the chair. So my question is that, so you showed that option 2 was best, and if the figures I remember is right, 35% played chess and 33% sat on the chair. I'm interested to know what's like the overlap, because my thought process is that do the human trust the chair which moves to sit down on it? Like they might appreciate the technology, but do they have the faith that it will not move away while they're sitting on it or something like that? How's the social response to this kind of dilemma?
Yeah, I mean, it's a great question. So when you run a human experiment, and I really like behavioral variables, like you can give surveys of be like, what do you think of this? And then people can do self-reports. But when you can actually put the robot out there with different permutations and see, well, which one works best for them literally coming and playing a move of chess, them literally walking towards this system, because as a proxy for attention and so on. So are some of those behavioral metrics correlated? In this case, they seem to be. You know, a scientific method requires you to change one thing at a time. And, you know, all of these things are kind of correlated. And we didn't do a lot of interviews. I think we did like a 10%. We followed people and be like, hey, would you like to talk about that interaction that just happened? Like, why, like what? So we did get some conversation with people to help interpret some of the responses. But in this particular case, going to the table was highly correlated with sitting on the chair and playing the chess move. But it's smart to run the statistics to kind of numerically prove that. So that's a great question.
Yeah, thanks.
Yeah. Cool. Well, we're here at noon. Any last burning question? All right. Well, thanks for coming. All right. Take care and have fun making social robots.